Hello everyone, it's contest 5 today. Pretty good results. I expected it to be a little bit easier than the previous one because previous one was kind of hard one. So good results. Everybody done pretty well. Let's see what we've got. So first problem was very easy. So it's supposed to be easy. Sometimes problems are just like this. So you have two lines. Okay, let me so you have two strings. You need to check if the second string is just reverse first string. Yeah, that's all. No tricks here. That just what you need to do. Just read two strings, check if one is reversed another thing. Actually, let's try to solve all the problems today. And just for fun, let's try to solve all problems. So let's check if I actually can do it. So the first problem is really easy. So we have two strings. Let's say string A and B. Let's read them. And then check if one is reversed another. So I will reverse one of the strings. Reverse A begin A end. And check if A equals to B. Then output yes. Else output no. So that's the whole solution actually. So this problem is supposed to be easy. I hope you didn't have any problems with this. Okay. No, let's see. So no, a lot of people solve this problem pretty fast. So did someone have problem? Okay, why you may have problems? I'm interested. Why you may have problems? So that's 42. Okay, how did you get this result? You kind of overcomplicate things. Okay, so yes, you check. Okay, go from the left. If they're not equal, that's the same. And why doesn't work? Because you may have strings of different lengths. Yes. No. Okay. So in this problem, they didn't promise you that your strings have the same length. So you also need to check this. And because you only check as one size, so you go from one side. So when you finish one of the strings, another one may have more letters, and you don't check them. Okay, that's nice bug actually to have. Again, you need to be careful when reading statements. If they just say I have word S and word T, and then don't promise you that they have the same length, then the empty length do not exist. So they only say that length don't exist, and all examples have the same length. Okay. So sometimes again, okay, this may be a trick in this problem case. Sometimes the problem authors, they just have some small trick in the statement and then don't spoil it in the examples like here. So that's all. That's problem 1. Very simple, very fast. Let's take problem 2. Problem B. Problem B has, again, this is long implementation problem. It's easy problem, but again, you have a long problem statement. You need to read it. You need to understand it. But the problem itself is really easy. So again, I have some pairs of strings basically. Yeah. So first string is a name. Second string is a like status. How do you change this? This name of the crew member, status. Okay. So I have name and status of each person on the ship, and I need to output them in some strange order. And like this statement explain you in which order you need to output all these names, and you just follow this. Let's just do it actually. Let's do it really quick. So I have let's just read them all. I never use long names for variables actually, it's only for you. So I read names and status, and then just implement what's going on. So first arrays. And let's do it like this. So I will go for check if status e equals red, I will output name. And now I'll just repeat. So you can do it in clever way. You can make some array of possible statuses in which order you need to output them, or you can just copy paste this code multiple times. Because it's easy problem, I will copy paste. If it's little bit harder, I will put all these statuses in array and just make an outer loop for all these situations. But this problem easy. I will just do it like this. So actually, woman or if status equal child and children and captain. Yes. So red, woman, child, man also. Okay, man, and finally captain. Let's copy it from here. Oh, we have Jack as the captain. Nice. Nice touch to the problem statement, actually. I believe that's it. Let's copy. Okay, let's try it on examples. Just to be sure, I'll copy this here. Looks fine. Copy. Boom, 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 boom. Submit. Okay, that's all. That's problem 2. Again, no tricky algorithms, no any special ideas. Just carefully read the statement, implement what's needed to be implemented. Good. That's all. Let's check your solutions probably. So let's pick some fast solution. Let's pick something from the middle. Let's pick you. Oh, okay, and that's another way to do it. So you just make an array, and you instead of traversing multiple times through all persons, you just put them in like 4 different buckets. Yeah, so you put this in bucket 0, this in bucket 1, and then output them in this. Nice solution. Yeah, you can do it like this too. Good. 8 minutes. That's a good result. Third problem actually requires some idea. So they didn't tell you what exactly you need to do. They tell you like the problem statement actually. So you have some problem. So what we need to do? You need to understand what's going on. So again, we have number n. So input is a single integer n, and we need to output the string of size n. And here you need to understand what is the property of the string. The property is you don't have any palindromes of size 3. Specifically 3. So only palindromes of size 3 matters. You may have palindromes of size 1, 2, 4, or anything else. But no palindrome of size 3. Palindromes of size 3 is very easy string. So it's like string like ABA. So you need to build a string which doesn't have any substring of this type. And from all such substrings, for all such strings, you need to minimize number of letters C in the string. So you only have letters A, B, and C, and you want to minimize number of letters C. Good. Now, by looking at it again, if you play a little bit with this string and see how you construct strings without palindromes of size 3, you just construct them from left to right. So I want to avoid letter C. Yeah. So you go from left to right. You have letter A, then you have letter B because I want to avoid C. Yeah. Well, here, this position I can only put. I cannot put letter A. So this shouldn't be equal to A because then I will have palindrome. But I want to avoid letter C, so I can put letter B. Now here I cannot put letter B because I will have palindrome. Yeah. So I can put letter A and so on. So every time you have 3 letters and only one of them is forbidden. So you always can put letter A or letter B. And you continue A, B, B. And after you play a little, you see, okay, this string actually satisfies all the constraints. So if I continue like this, I can make letter of any, or I can make string of any size without any palindromes of size 3 and with no letter C. And that's actually the whole solution. So you just construct string like this, and it's that's it. Let's implement it really quick again. As we implementing everything today, let's I'll do it like, or you can just output. Okay, let's put them in a string just for clarity. So I will do it like this. Let's simplify it. Let's say let's have AABB like this. So you can see I have period of size 4. Yeah. So I will get 0, 1, 2, 3, and then again 0, 1, 2, 3, and so on. Yeah. So I have period size 4. So I will just do it like this. Okay? I will say equal. I will AABB of size A modulo 4 like this. That's it. That's the whole solution. Let's again submit it. Any questions by now? So it's okay. This problem was supposed to be kind of easy, but again, they require at least some reading. So you need to read statement, you need to understand what's going on, and problem C actually require you to think. Yeah, that's good. So you can make so it's actually you have. IBC. Okay, so you were close in this submission, but you think you also need letter C. You don't. You can continue with AABB. Good. So you can understand the whole structure. So it must be repetitive, but just pick the wrong string. Yeah. Pretty close, but then you fixed it. Good. What we have in problem D? We have 2 sequences. Yeah. So we have sequence like this, and we have sequence like this. Basically 2 arithmetic progressions. What we need to do, we need to find the first element which appears in both these sequences. Do we have explanation? 82. Let's try to solve the first case just by hand. So in the first case, I have A equal 20, B equal 2. So I have first sequence is 20, 22, 24, 26, 28, and so on. Yeah. And the second sequence starts from 9, and step is 19. So I start from 9 plus 19. Oh, it's really hard. Why it's 82? So again, 19 plus 8 plus 8, 28. Okay, I misread the statement. It's also B plus A. So okay. That's why you always read the samples. Okay, so you read the examples, try to understand why I have this answer. Maybe you misunderstand the statement. Okay, so B is the start and A is the step. So I start with 2 with step 20. 2, 22, 42, 62, 82, 102, and so on. And the second starts with 19 and step is 9. So it's 19 plus 9, it's 38, plus 9, it's 47. No, plus 9. 28, 37, 46, 55, 64, 73, and 82. And here we have the same element. Oh. Good. So now when we understand what's going on, let's just think. So you think that what you can see in this statement, another thing that you need to pay attention on is their constraints. So all the constraints are very small. So all the numbers are very small, up to 100. When you have numbers up to 100, It usually means that everything is kind of small in this problem. So all these numbers are kind of small. So maybe this common number will appear pretty soon. And you can actually see that's correct. So if you so what I need to find? I need to find. So again, if you look at it like this, so I have 1 points with one step, with step A, and have another points with another step, with step C. Yeah, and this point is B, and this point is D. Okay, if you didn't know it before, then you may learn it now. So if you have a situation like this, then actually the whole this situation will have a period. Yes. So if you start from here, let's find when we have the same position, like from here. Let's find when we have, let's say here. So at some point you will fall to the period. So whole this picture is kind of periodic. Yeah. And what is the length of this period? No, if you look at length of this period, let's say x. X should be divisible by A, and it should be divisible by C. Yeah. So this length of the period is actually lowest common ancestor, multiple. It's least common multiple of these two periods. Yeah. So situation is always periodical, and the period is the lowest common ancestor of these two, or lowest common multiple of these two things. Okay, is it clear why is it true? No, it should be kind of clear. Yeah, no, that's because if you have any segment of size which is divisible by both A and C, then inside this period you will have like integer number of periods of the first type and integer number of periods of the second type. Yeah? So if x is divisible by A and x is divisible by C, then you will have a period. Yeah? No, lowest common multiple is at most A multiplied by C. Yeah? And you see here, then they both equal to 100. So in our case, it will be at most 10,000. Yeah, so it's kind of small. So we have a very small period. Now what can you do? You can just check it. So what one of the possible solution is to try to find it just using brute force. You just check all possible points and check if both progressions have point here, or you may build these two sequences. Like build first 100 elements of both sequences. 100 will be not enough. You can build first 10,000 elements of sequences. That will definitely be enough. And just check. So you build these two sequences. And check if they have a common element. Also possible. Actually, this problem is solvable in better time complexity. So you can solve this problem even if you have big numbers here. You do it using something like Euclidean algorithm. Again, like when you build lowest common ancestor, you can also find this closest point using kind of the same trick. It's a little bit tricky because I have starting points here, so you need to be care about the starting points, because when you run Euclidean algorithm, you may run to a point which is like below here, so you need to be careful. But it can be solved in better time complexity using Euclidean algorithm. That's my point, but it's not required here. You can just try all points and check if it's fine. So for example, you can do it like this. Okay, let me do it really quick. Boom, boom, boom. A, B, C, D. I will just do it like this. I will check all points. So I will do for loop for int e from. So what is the minimal? Minimal value will be maximum of B and D, right? So that's the minimal point. So when both sequences already started, A equal to, let's say 20,000, just 100,000, just to be sure. So if you're not sure which number to put, put the maximal number that will fit into time limit. That's actually good advice. So if you're not sure which number to put here, you think 10,000 should be enough. No, put 20,000. Just to be sure. Why not? Now I will check if this I belong to sequence. How I check it? I need to check that I minus b is divisible by a. Yeah, then it belongs to the sequence. And the same for the second. If I minus d is divisible by c, then I will output I and return 0. Yeah. If it never happened, then I will output -1. That's all. Let's check. Come. Someone asked me so is there any constraint on number d on the answer? It's actually that means that this question means that you're thinking in correct direction. So I hope you solve this problem, Roman. Let's check. You didn't solve it. Let's check why. Sorry, I didn't spoil you this. It's kind of the same. Infinity is too much, but you don't need the you want to start from B. Okay, makes sense. So you want to B. Why you smooth like this? You start from B. You need to start from maximum of B and D, and you swap them. It's A less than C. You need to swap if D is less than B. Yeah. Here, I believe you need to add here like maximum of B and D, and it will be fine. Let me fix it really quick for you. Again, pretty close to correct submission. That's good. Let's say maximum of B and D, and I'll just so you put here the number that you so here you make you want A to be a big step. Because you have step of size A. No, it may not work. So if you may have step 2 in so I believe the worst case for your solution is like this. When I have when step is 2, so both A equals C equal 2, but they're misaligned. So like B equals 1 and D equals 2. So I have steps 2 like this and steps 2 like this. So they never have the common point, but both A and C are small. Then you have a very long loop here. Let's just decrease this mean. That should be fine. Can I do it from the first try? No, I can't. Why? Plus A because okay. Sorry, I'll resubmit it again. Okay, if you do it like this, okay, let's do it like this. So start from B with step A, but I will check one with small. So if D is less than B, that should be fine. No, not again, come on. Oh, sorry, it's so embarrassing. You need to take maximal one, not minimal one. Okay, that's the problem of bad code. So when you have bad code, it's really hard to fix it. So you just sometimes easy to rewrite the whole code. So I want B to be the maximal one. Yeah. So if B is smallest one, then we need to swap. Sorry. We try to write code which uses as little tricks like this as possible. So when you need to do tricks like this, it just means that it will be harder to debug. So try to make code as simple as possible. Okay, let's just show you my code as well. If you produce short and simple code, it will be much easier to debug. It's not always so. You need to make it simple, but not too simple. No, you need to find a balance, but you will do it with practice. What we have in problem E, we have some sequence of integers, and we need to split the sequence into segments. For each segment, we need to be good. And good just means we have two elements of the same, two equal elements. Yeah? So we have basically an array of types, and we need to, in each segment, have at least two elements of the same type. Yeah? Like here we can just take the whole segment. Here we just can split it into two segments, from 1 to 3 and from 4 to 7. Well, again, how you solve problems like this? No, you think, how would I split this array if I need to do it by hand? So I want to split array into segments. Each segment should contain at least two equal elements. So let's look at the leftmost segment. So let's look at the leftmost segment. So it starts here and ends somewhere here. I want at least two equal elements in this segment. So I go from left to right and find the first point when I see two equal elements. So at the first time when I see element x, which is already here, now I have a good segment. Yeah. So again, you start by having small segment, then you increase it until you have good segment. Yeah? So property of being good segment is kind of monotonical. So when you add more elements to your set, it can become bad. Yeah. So if you have good segment, if you put more elements in your segment, it will stay a good segment. It is a good sign that you can do something like grid algorithm. Yeah. So if you have some property, and this property is kind of monotonical. So when you have small set, it is bad. But when you increase, at some point it becomes good segment. And when you increase it more, it stays good. Yeah? And you can do something like this. So let's see. So you had bad segment, then at some point it becomes good segment. Now, what you want to feel that it looks like it's always optimal to finish it here. So if I have some first segment, and it is so it will finish. Why? Because if I have any other segment here, imagine you added more elements. So you added this x plus something else. Then you take the next segment and just move this border to the left. So it's here. Yeah. So my segment is still good. This segment is also good because it was good before. So when I move this border to here, it stays. It is still good. Yeah? Because when you extend segment, it stays good. The only problem is with the last segment. For the last segment, so again, the whole solution works like this. So you go from left to right and pick the first point when you have the element which you already seen before. So when you see the same element for the second time, so I have x and x again. Then you stop your segment, start the next segment, and again. Then again, stop when you see the element which you already seen before. Then you step reset. The only problem is with the last segment, because it may happen that last segment is bad segment. Yeah. What does it mean? It means that you cannot do any more good segments, because again we prove that every segment can be stopped here. Yeah. So what we do instead, we just extend this last segment to the right. So we just extend it to here and have a good segment to the end. Again, that's only because we need to split the whole array. So we need to split the whole array into segments. So we kind of build some segments, and if we have some rest elements, then we just add these elements to one of the segments, and just easy to enter to the last segment. Clear enough? I hope it was clear enough. Let's do it really quick. How do you check if you already seen the element? Easiest way is to use sets. So I will use sets here. Just read everything. Boom, boom, boom. Now, the plans. I go from left to right. And remember which element I already seen. Yeah. So I will maintain set of elements which I already seen before. Then I check the next element. Check if I already seen this element before. In C++, you do it like this. You say if s find e is not s. So that's how you check in C++ with you. What do you need? Are you can? Oh. Thank you, C-Line. I'm not that good in C++. Maybe they added it in some versions of C++ and I missed it. Okay. You learn new things every day. So you check if its element belongs to this set. Then you need to stop your current segment. Yeah. So let's maintain a vector of possible segments. So this will be my result. I will add my segments here. So I will add new segment. So I need to remember the left border. So left border initially will be 0. So my current segment will be from my left border to element I. Like this. So I put new pair to my segment list with from L to I, and move the left border to I plus 1. I will do inclusive for simplicity. So, okay. And you need to reset your set. So you move to the next segment. Yeah. So you clear your set, initialize left border, and put the current segment to this. That's all. Now you just add your element to the set. That's all. So now we build all these segments. Now in the end, we need to check if the answer is -1. So sometimes answer is -1. It just means you the whole array is a bad segment. So you don't have any pair of equal elements. So we'll just check if this array is empty. Then I'll put -1. If not, then I will add all the rest elements to the last segment. I will do it just by changing the right border of the last segment to n-1. Yes, I will say res back second equal n-1. Yeah. So I just extend the last segment to the end, and you just output the result. So I output number of segments. Let's do it like this. Not the best way to do it. Good enough. I do +1 because here everything from 0. I need to output from 1. That's all. Check. Boom. What? I didn't read that. Okay. Makes sense. I forgot. This makes sense. Good. Again, not very hard problem, but it requires something. So you need to again, I will repeat it every time. You need to read the statement and understand what's going on. After that, you understand that greedy algorithm will work, and greedy algorithm will work because you have this property that if you extend the segment, it will stay good segment. Yeah. So longer the segment, it's still good. So like monotonicity of this. And that's why you can extend the first segment until you reach the point when it's good. And you don't need to extend it further because the next segment will stay good. If you don't need to move this border to the right because you will make the next segment only worse. Yeah. Let's check how you do it. Let's check. I always check you because. Overcomplicated. Okay, so basically here you implement the set by yourself. Don't need it. So you take all the elements, sort them. Yes. Remove the unique elements, and here you make lower bounds. Basically you do all these things just to maintain set. I believe. Yes, and here you check if you're seen or not seen. Yeah, it's also possible, but it's just overcomplications. So what we're doing here is like here from it. So this part we're doing the something with the value compression. So the problem is we have pretty large values in this array. So size of the array is small, but the values are pretty large. So what we're doing here, we're going from large values to small values by just renumerating everything. So instead of let me show you. So what we're doing here. So imagine you have array A and you have some numbers here like 10, and then we have 25, and then 7, and like 103, and something else, 84. Yeah. So you have big values in your arrays. But so what you can do instead, you can let's pick some similar values. So some equal values here. So what I want to do, I want to go from this array to another array with the same properties, but small values. Yeah. So what I will do, I will sort all elements. I will have 7, 10. Oh, okay. So here I'm doing sorting. Sorting, then removing. So let's do it in 2 steps. I first sort elements. I have 7, 7. 7, 7, 10, 10. Oh, 10, 10, 25. Yeah. Then I remove. You remove unique elements from this array. So you have from this unique basically removes duplications. So I have 7, 10, and 25. And then you put in array A the position of your element in this array. So you have this array vals. This is real. And then you replace your elements with these positions. So you have, instead of 10, you put 1. So this will be 0. This will be 1. This will be 2. Instead of 25, you put 2. Instead of 7, put 0, 1, 0. This is a pretty common technique. Good thing that it not only, so for this problem, it's important that it preserves the equality. So if we have equal elements here, so we have like 10 and 10. Then in this modified array, you also have equal elements. So if you have equal elements in your initial array, you have equal elements here. What's more interesting, it preserves also the relative. So which number is smaller, which number is larger? So how it's called? Comparability. Comparability, is it the word? Probably yes. When you compare the elements, you have the same results. So if 10 was less than 25, then in this array 1 is less than 2. So if you take any pair of elements, they will compare the same way in the initial array. So this is more important. So it's like common technique that you use when you want to move from large values to small values. So it happens when you don't care about values, but only about the relative values of something. So you care about which value is smaller, which value is larger. Then you can do it like this. Okay. Yes. And now, after we do it like this, instead of set, we can use just simple arrays. So we use arrays just to make marks of these elements which we've seen before. Again, a good solution. It may be even faster than mine, but you don't need to do it that fast. It's a little bit overcomplicated for this problem, I would say. Oh, problem F is about chess. So chess problems is like the whole area of interesting problems in competitive programming. So they used to happen a lot. Now it's a little bit, it's a little bit rare situation when you have problem about chess, but still it happens sometimes. Maybe some people who good in chess have some advantage in these problems, but I don't think so actually. So the important thing, if you have at least some knowledge about chess, about the chess pieces and how they move, that may be a little bit advantage. But I believe that all children nowadays know how to play chess, at least know how to move pieces. So it's not that big advantage for you. Good. Now let's go. So what we need to do? We need to check if there is a check. Okay. So we need to check if one of the black pieces attacks the white king. So we have white king and several black pieces. We need to check if these black pieces attack this white king. At least one of them. Yeah? So if at least one black piece attacks the white king, we print yes. If no, we print no. The trick is, again, they show it in example. Thank you very much. So sometimes authors are that kind, so they show you the tricky situation. So in this situation, you have no. So you have this black bishop, which kind of attacks your king, but this black rook, it blocks this attack. So this bishop cannot attack this king because there is this black rook in the way. So, and you need to check this. So this is the trickiest part of the situation of this solution. Yeah. So if not this, then it's kind of trivial. So you check if your rook is in the same row and in the same column, then you say yes. If you have bishop in the same diagonal, you print yes. Yeah. But this is the only tricky situation when you need to care about. So what you do? You can, okay. The trivial solution is like this. You check all the, okay, trivial solution. The trivial solution could work like this. So you have this white king. Good enough. Okay. Something like this. So you have white king. So you have iterator all black pieces. So if you have like black rook here. Sorry, I'm very bad in drawing stuff. So this is rook. So if it is in the same row, then you need to check if there is any bishop which stands between them. And if you do it using brute force, then you need to iterate over all rooks, then iterate over all bishops to check if it is in the way. The problem is number of pieces is too large. So we have like up to 10 power 5. Up to 500,000 pieces. That's too much. Yeah. So if you iterate over all rooks, then over all bishops, you have like 250,000 square. That's too much. It will time limit. Yeah. And I believe some of you actually get this time limit, because yeah, it is like this is the first solution which comes to mind. So you check the piece which attacks you, the king, and check if there is nothing in between. Yeah. So we need to find a little bit faster solution. Again, how do you think about this solution? Let's look from another side. So let's look from another side. So I have this king. Let's see who can actually attack this king. So they may be a rook. So if the rook attacks this king, or a queen. So well, queen is just a combination of rook and bishop, doesn't matter. So I will talk about rook and kings, rooks and bishops. Yeah, and queens are kind of both. Yeah. So queen can attack from one of these 4 angles. Yeah. So queen can attack from here, or rook can attack from here, or from here. Yeah. And the trick is that only one rook can attack from every angle. So you only care about the closest piece in this direction. Yeah. So only one piece from each direction will attack my king, and this is the closest piece. Yeah. So you can find the closest piece in all directions. This is the bishop. It's okay. You can't tell, but it is bishop. So because it doesn't have this. This I don't know how to call it. Yeah. So if the closest piece is a rook, then you are on the check. Yeah. If the closest piece is a bishop, then this bishop blocks everything besides. So it doesn't matter what happens here. Yeah. If you have a rook here, it will be blocked by this bishop. So you go to all directions, find the closest piece, and check if this piece is a rook. Now, how to find the closest piece in this direction, for example? No, it's easy. You find all the pieces in the same row. Yeah, so you check all. So you have multiple pieces in the same row. It is bishop. It is another rook. I could use some letters instead, yes. Okay, it probably will be better to use letters, but not drawings. My drawings are all awful. Okay, so you have some pieces in the same row. So you take all these pieces, which in the same row and to the right from each. So let's find all the pieces in this area. In the same row to the right from the king. Yeah. And from all these pieces, you actually care only about the leftmost. Yeah. So I look at all pieces in this area, find the leftmost. If it is a rook, then it attacks me. If it is a bishop, then it blocks all attacks from the right. Then do all the same in all other directions. What about diagonals? Same thing. So you look at diagonal here, and you have 4 diagonals. In all diagonals, again, you look at all pieces in this diagonal, find the closest one. If this closest one is a bishop, then it will attack you. If it is a rook, then it will block the way from all attacks. That's all. So we have 8 possible directions of attack. Yeah, and we look at all directions and check which piece is the closest in this direction. If this piece can attack us, then we have a check. So how to implement? Let's try to implement. Implementing this is actually another challenge. So after you understand what you need to implement, let's try to implement this. And so I have coordinates of my king. Let's say kx, ky. And I have coordinates of my pieces. So let's say vector x and y and let's say vector of string. I'll just put all of the names. Oh, they're single letters, but it doesn't matter. I'll just do that. Like this. So you read all the data. Now. Let's go. So let's start. Let's just implement this. I will just implement this picture, okay, and then I'll show you how to do the rest. So what I'm doing. So let's say. So which one is x? Which one is y? Let's say I have x here and y here. It doesn't matter which. Just spacing. So I will check positive coordinates by x. Yeah. So I'll check for check if I need to check if this belongs to this area. Well, I'll check if y equals to ky and x is greater. No, it should be greater than kx. Yeah. And then I am in this area. Now, from this area, I need to find the leftmost element. So, again, how you find the leftmost element? You find the optimal one. Let's say j equals -1. Then say if j equals -1, how you find minimums? You check if you don't have minimum, or your element is better than the previous minimum, or if xy is less than xj, then j equals 9. That's how you find the minimum. Yes. So you initialize minimum of some impossible value, then check if you have no minimum, or if your next element is better than your previous minimum, then you update your minimum. Now in the end we check if j is not -1 and the state of this j is rook, or if state is queen. Then we say yes. So that's how we check this one direction. So now I checked only this direction. Now we can check. Now you need to check just all other directions in the same way. Let's try. What you can do? You can just copy paste this code 8 times, and just check it, change it a little every time. It may work, but it will be a lot of code. So here is it not very easy, not very simple situation. So I have like 10 lines of code. If you multiply it by 8, you have 80 lines of code. 80 lines of code, it's a lot to debug. So if I have any mistake here, I need to find this mistake. And when you copy paste and change them something, you may make some mistakes. What you can do instead? Okay. I'll write 2 pieces and then we'll compare them. Okay. Let's check one diagonal for constraint. So let's also check one of the diagonals. Let's say this diagonal, for example. Let's see which one. Let's check this one. I'll just do it like this, so I don't reuse this j. And just copy it. So when you have diagonal, so you need to check if the element belongs to the same diagonal. Diagonal just means that x, y plus. Let's rewrite it like this. Let's say that so element belongs to the same diagonal here. If this difference equals to this difference, yes. So I will calculate difference by x, difference by y. If it is the same, yeah, then I will do. So I'll say difference by x is xi minus kx. If it is the same as difference, so ky minus yeah, because I move in this direction. So here you positive, here negative. And let's actually let's try this. So let's say that let's say like this. Let's say dx equals to you'll see actually what I will do in a second. Yes. So I will say if dx equals to minus dy. And so this total shift will be like dx minus dy is positive. Minus dy because dy is negative, yes, in this situation. So x goes to the right, yes, and y is go up. So I'm going right and down. So x goes in positive, y goes to negative. So if I have the same shift and the distance is positive, then I will update. Yeah. Actually, let's put this to another variable. Now, if I don't have minimum, or if my element is closer, no, it's called min d, okay. It doesn't matter actually, because I check here. Then I update min d, like this. Okay, it does look overcomplicated or not? Okay. Is it clear? Because I may overcomplicate sometimes. Because I already think about how I will unify anything. You'll see. Here I see if it is no -1 and if it is bishop or it is queen. Okay. Now let's try to unify these two cases. So, can I increase the scale a little? Oh, so both of them fit. So let's try to good. So let's try to unify this thing. So let's try to write both these cases in a similar way. So I will do it like this. So I will copy this here. Boom, 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 boom. So here, I need to check that y is the same. So I just need to check that dy equals to 0. Good. Now I will rewrite this to make it similar to this. I will write like this. I will say dx plus dy equals to 0. Okay, watching me. I will tell you what I'm doing in a second. Now this distance will be calculated differently. So distance will be calculated just like dx. And this part I will just copy paste from here. Now I can copy paste this part from here. No, not this part. I need to copy min d. Okay, copy. Now, see, good. Now, see what difference in this part. So these parts are kind of similar. What's the difference? Difference is how I calculate distance. I will just mark it with breakpoints. Yeah. So here is difference, and here is difference. Pop. Yeah. I differently check that my element belongs to the same match, but we can actually unify. So we will just in both these cases. So what happens? So here, when I calculate distance, I multiply dx by something and multiply dy by something. So here, I will do it like this. So x multiplied by 1 plus, okay, I just want to show you what I'm doing, how I get to this situation. Then I will tell you what is the easier way to do it. Dx by 1 plus dy multiplied by minus 1. And here, you see, so here I multiply dx by 1 and dy by 1. But here I multiply dx by 0 and dy by 1. Okay, it doesn't look easier than now, okay? But now you see that they are kind of similar. The only difference is in these constants. So here I use constant y and 0, 0 and 1. Here I use 1, minus 1, 1, 1. See? So I will simplify it now. So I will just run the same code twice, putting different constants in these positions. So instead of having 8 copies of the same code, I will have 1 copy, but just put different constants in these positions. It actually helps in this problem if you're good in computational geometry, surprisingly, yeah. Because what I'm doing here is actually calculating dot product and cross product. So because what I'm doing here, so if you're good in geometry, then what I'm doing here, if you have direction, so you have a starting point and you have a direction, and you need to check if another point belongs to this direction. So let's say direction D. Let's call it D. No, okay. We have already D. Let's say direction A. We have array A. No, I don't have array A. Let's call it A. So let's say it's A is my direction. Okay. And you have this point. So vector from your point to the point you're looking for is B. Yeah. So if you need to check if this point belongs to this array, you need to check if cross product is 0. Yeah. It just tells you that a point belongs to this line. Yeah. So it will tell me that this point belongs to this line. Yeah. And also you check that dot product is greater than 0. It tells you that this point belongs to the positive side of this vector. Yeah. And that's exactly what I'm doing here. If you check, so I check that. Okay, I forgot to check this, to change this. I'm going to check the distance. So this D is basically a dot product, yeah, or scalar product in some ways. So this the D is so here my direction is again, first case is when I look in this direction. So my direction is vector 1, 0. Yeah, in this case. So here I'm having dot product, see, and here I have the cross product. Good. And in the second case, if you remember, move back. In this case, I have vector which goes to the right, which positive, x is positive, y is negative, so minus 1. And again, if you look here I have dot product, here I have a cross product. Good. Okay, so again, you may not know all this stuff. It doesn't matter. So you can just copy this code 8 times and modify it. I just tell you what is the easiest way to do it, and it will be much easier to implement and much easier to debug. So what I will do, I will put all these directions in array. Years. So what directions I have? I have direction 1, 0, minus 1, 0, 0, 1, 1, 0, minus 1. That's for the rooks. Yeah. And I have directions for bishops. It's 1, 1, 1 minus 1, minus 1, 1, and minus 1, minus 1. In some strange order, but it doesn't matter. In some order. I don't care about the order of these elements. I just need to. Now I will iterate for all. I call it A. Okay, in divs. Okay, hope you're still with me. That's some math. So the code is easier, but it's a little bit more intellectual now. Yeah. So okay, hope you understand. What I'm doing here. Here I'm calculating the dot product. Yeah. So distance again. Dot product basically is the distance in corresponding direction. So like the meaning of dot product, not the meaning, like the easiest interpretation of dot product is the distance of the vector in corresponding direction. So I will multiply dx by a first. Oh, let's call them actually x, x, y, y for simplicity. So multiplied by xx plus dy multiplied by yy. So this is dot product. And here I calculate the cross product. So I'll multiply dx by dyy minus dy by xx. Again, I check if cross product is 0, it means I belong to this line. And check if d is that's distance in this direction, just this dot product. Good. Now here I need to check if it's okay. It must. I need to check which one is rook, which one's. I don't want to do it. Okay. But we need to check if. No. Okay. If it is one of the first four, okay. So I check it if it is one of these first four shifts, yeah. Then it's rook, or if it is bishop. Yeah. That's all. That's the whole solution. So you see, it's quite short if you implement it correctly. And that's like the whole trick of the problems like this. You try to simplify your solution to the point when it's easy to implement and it's easy to debug. So maybe I have bugs now. So let's check. Yes. No, maybe not. So if I have bug, we will have some fun time to debug it. Let's check. Okay, not today. Yes, today. Do I have overflow of problems? May I have overflow problems here? It's close. No, yes, I will have overflow problems because okay, the distance, okay, difference in one coordinate may be up to 2 billions. Yeah, so when I sum 2 billions twice, I have 4 billions. I hate my life. Okay. Let's do it in minutes. Okay, this is actually expected problem. I could avoid it. I have defined if you don't remember. So my longs are 64 bits. Uh-huh. Okay, okay. That was avoidable mistake. Good. That's all. That's problem F. Again, tricky problem, both tricky in algorithmical way and in implementation in programming way. So you need to find the fast solution because the trivial solution will time limit, and after that you need to find a way to implement it in short solution without bugs. So it's tricky problem. So it's if you solve this problem, good for you. Problem G. What we have in problem G? We have some array, and we need to shuffle it. We need to shuffle it in such a way that we have many. Basically, so we have array. So we make array of pairs. So all elements in the left part is some shuffle of this array, and all elements on the right part, some permutation of this array. So we put some permutation in the left column, some permutation in the right column, and I want to make as many pairs of non-equal elements as possible. Well, let's check for example first example. In the first example, we can make all pairs different. Like we put 6 pairs and put them like this. So we shuffle elements here, and we have all pairs are pairs of non-equal elements. Let's see when it is possible. When it's possible to make all pairs good pairs. Let's think. So when it is impossible. Again, it's quite trivial to say that the answer is always okay. Let's say answer is k. K is the answer. So it's quite obvious that k is not greater than n, right? Because I have n pairs. Because at most n of them may be good pairs. Let's check how to check if k is good or if k equals n or not. So when I can have all pairs different. So let's first think when it's impossible. So when it's impossible to make k equals to n. And you can see the second example when k is not equal to n. And here n equals 4, but I can make only 2 pairs. Why is it so? Because I have a lot of equal elements. So I have a lot of 1s in this array. Yeah. So I have a lot of 1s. I cannot make many pairs of different values. Let's try to generalize it. So how we generalize it? We check. So if we have array A, let's see array A. So the problem is when I have many elements. So it's C. Okay, let's rename it to C. So the problem is when I have a lot of elements of the same type. So how many elements should it be so it becomes a problem? No, obviously, so if it's more than half of elements, yeah, then I can only make these many pairs. So these elements of type X I cannot combine to anything only to these elements. So the maximal possible number of pairs I can do is this amount of elements here. So these elements are not X. Yeah. No, it's easy to see that in this situation, it's actually true that this number of these elements is your answer. So you can make this number of pairs. So if more than half, so if this is more than half, then this is your answer, because you can do it like this. You can reverse your array. You can take this array. You can reverse it. No, 2k. Okay. So you can reverse it. You can assign these pairs will be good pairs, these pairs will be good pairs, and now you have a lot of elements equal to x, you can do anything about it. Yeah? So this is the best you can do. Yeah. So let's look at the element with maximal. So let's say number of elements here is, which number we don't have? P. Yeah. So let's say P elements of the same type. So P is the maximal amount of element of the same type. So we check. So if P is more than half of n, then the answer is just number of pairs will be twice n minus P. You do it just by reversing the array. You take your array, reversing array, assign this to this, this to this, you have the array. What if not? What if not? What if I don't have any element which occurs more than half of the element mass? So if I don't have any value which occurs may have more than n over 2 times, then you think, okay, so this is, so what is the border case here? The border case when let's see. So if P equals to n over 2, yeah, what will happen? I have some half of the element equal to x and half not equal to x. Yeah. Some elements not equal to x. And again, you can just you can do the same, reverse the array, put these elements here, put these elements here, then answer will be n. Yeah. And then you think, what if I have less than half elements? What if no element occurs more than n over 2 times? It looks like situation is only better. So if I have more different elements, it looks like situation is always only better. It's actually true. So what you can see that if P is less or equal than n over 2, the answer will always be n. Okay, this is a hypothesis. And then you think, how would you do this? Again, you have some elements. Let's group them by the same value. So we have 1, 1, 1, 2, 2, 2, 3, 3, 3, 3, something like this. And none of them occurs more than half of the n. Yeah? So I want to shuffle these elements in such a way that every element is assigned to some another element, not equal to it. Yeah. And again, that's more than a mathematical puzzle for you. But if you never saw something like this, that's okay. I'm not sure how you can come up with a solution if you never saw it before. You can just play with this array and think what you can do. So you need some I don't know how to explain. So you need to come up to some solution which kind of so you think it's always possible. Yeah. So your hypothesis, it's always possible to construct the array of size, to construct the answer of size n. And you think how it's possible. No, you may think about different situations. You may kind of connect the most. So the problem is that the most frequent number. So you may think in this case, you may take the most frequent number and do something about it. Depending on what you do, you may come up to correct solution or incorrect solution. It depends. The easiest way to come up with correct solution is actually to think about some stable transformation. So you take your array and try to do something which you can explain. Okay, like reverse array, shift array, do something like swap some parts of this array. So some simple transformation. Sometimes it works, sometimes it don't. So sometimes you need to do something more sophisticated. But in this case, the answer is pretty easy. So what you need to do is just to shift all elements to the right by the half of the array. So you calculate half of the array. So I have array of size 9. Yeah, so n equals 9. So I just shift everything 4 positions to the right. So I just make tum, and start from here. Start 1, 1, 2, 2, 2, 3, 3, 3. Yeah. So I start from here and just make like cyclic shift of my array. No, it's easy to see that it will not make any pair of equal elements, because if you have some sequence of equal elements, so then in this array it will be shifted to half of the n. Yeah. So difference between here and here will be n over 2. And since we don't have any element which is occurs more than n over 2 times, when you shift it n over 2 positions, it will not intersect the initial segment. So you have initial segment and shifted segment. They will not intersect, because the size of this segment is at most n over 2. That's all. Again, tricky problem. So if you never solved something like this before, it may be frustrating. So, but it's solvable. So you first you think that it looks like it's always possible if no element occurs more than half time, and then you try to prove why it's actually possible and try to find some constructive way to prove it. It's more like math problem actually, not programming problem. Programming part is actually pretty easy. I will show you. And m, why I don't need m? Okay. Just doing to make counters. Okay, to simplify. No, we just do it. Let's just make array of counters. Let's see m plus 1. Because from 1 I will do it like this. Don't do it like this. That's not best way to do it. But okay. Now I will check if I have if is more than half of n. So I won't do it like this, but I would rather multiply it here like this. So if some element is more than half of elements, then what I will do? Can I always shift it half? It's easy. I can solve the first case in the same way. No. Yes, I believe I can solve the first case in the same way. I'll just shift everything n over 2 positions to the right, and I'll get the same result. So let's simplify it. So I'll sort my array, copy it to B, and then shift it n over 2 positions to the right. You can do it like this. There is method rotate in C++. Like this. And then you just calculate the result. And print it. Okay, we don't even need these counters actually. Yeah, it's even easier. So you see here I have I rotated A. Okay, I rotated A. So this array to the right is sorted, and array to the left is the same array shifted 3 positions to the right. Okay? So you have 1 1 1 2 2 3. Yes, and here I have 2 2 3 and then 1 1 1. Let's go to the last problem. Where pretty close to finish. Okay, good. Come on. Okay, too slow, too slow. Let's go to the last problem. Last problem actually involves some data structures. So I usually try to not to put some data structure problems or some problems about specific algorithms, but this problem actually requires some data structures. What we have here? We have some row of pillars, and we move from the first one to the last one, and we do it by special rules. So we go from left to right. We always move in positive direction, so we move always left to right, and we can only jump if difference of heights is at most is greater or equal to d. So we only jump if difference is large enough. How do you usually solve this problem? So if I don't have this big constraint, so for small constraints, how to solve this problem? You solve it using dynamic programming. Okay, if you're bad in dynamic programming, just learn dynamic programming. It's not that hard. So especially for this problem, it's very standard problem for dynamic programming. So we count we're trying to find the longest sequence which is built up by special rule. So we have some rules here, and this rule dictates what sequence is good or not. And this rule this constraint on some consecutive elements of my sequence. So I have some constraints of what my consecutive elements of my sequence may look like. So from element 2, I may run from 3. From 3, I can run to 4. I can run from 3 to 4. I can't run from 3 to 4. I need to run from 3 to 5. So I can from 3 to 7 because difference is too small. So I only jump if difference is big enough. Yeah. So and you find the longest sequence which satisfies this rule. Yeah. Again, how do you understand this problem can be solved by typical dynamic programming? You see, you need to calculate some number of paths in some strange graph. In my case, in some sequences of elements. Yeah. And for this path or for this sequence, the constraint is only local. So the constraint is only about some pairs of consecutive elements. So when I construct this path, so let me show you. Let me show. So when you construct this path, you only care about the end of it. Yeah? So again, you try to construct some sequence. No, some sequence. It doesn't matter. So all problems the problem itself may look different, but the structure like this. So you construct some sequence, and you only care about some constraint about some pairs of consecutive elements. What does it mean? It means when you have some already constructed and you want to add some another element here. Okay, let's make it green. And you want to add some another element here. You only look at this element. You don't care about these elements anymore. It means that you can use dynamic programming. So your dynamic programming, so like the state of your dynamic programming only depends on this last element. Or maybe two last elements. Then you have like two-dimensional dynamic programming, something like this. Yeah? So if you have some local conditions, then you need, when you build your sequence or your path, you only care about the last few elements of this sequence. So how to do it using dynamic programming? Very easy. So let me implement you simple dynamic programming. Let's do it really quick. And boom, and the H. Okay, let's call it H. I see. Boom. And then again, how to do it using dynamic programming? I will make array D of size. I move from 1 to n. Okay, of size n. So D of n. I already have D. Let's rename it some x. Okay, I like use D for dynamic programming, okay? Who will judge me? Again, this value of D will be very easy. So it will be just best path and in E. So Di is the best path ends in I. Yeah. Okay, that ends. Okay. What is best path? It depends on the problem. In my case, I maximize the length. So it will be the maximal length of this path. Yeah. You go from 0 to n and just calculate it. First, you say di equals to 1. I always have path of I don't have path of size 1. You need to start from 1. Okay, you need to start from 1. Let's say d0 equals to 1 and from 1. Okay. Okay, I need some element here I will calculate maximum, so I'll just put int min because I will calculate maximum. Not good enough. Yes. Okay. Now you check which element may be the previous element. So you iterate all previous elements. Check if it's possible to jump from here to here. If abs of hi minus hj is greater or equal than x, then I can make this jump. Then di will be maximum of di and dj plus 1. I don't like it. I have int min. Let's say so if dj equals minus 1. That's more clear. Okay. What is it? Like this. Oh, now I like it better. So, so you put value minus 1 means there is no. No. Okay, let's move back my. Good enough. Good enough. So that's typical dynamic programming. Yes, you calculate the best path. You also need to output the path itself. Yeah. Let's check the first part first. So let's check. We calculate this number. So it's number 4. So let's let's do it slow. So we have some time. So let's 6. Okay. Now we calculate the path itself. So when we calculate the path, we just calculate the previous element in this path. So we'll have p and minus 1. So it will be the previous element in the path. I do it fast because it's just typical dynamic programming again. So I'll check if dj plus 1 is greater than di, then di equal dj plus 1, pi equals j. So it's previous element before. So if I cannot, and if there is no sequence. No, I can start from any element. Oh, my bad. I can start from any element. Okay, let's change it. So I can start from any element. And okay, in the end I need to find maximum. And now you print this path. So you print this path, you just follow this backward links you calculated here. Okay, I will do it like this. Okay, so it will be my path x. Okay, j. Okay, while j is not -1, I will say p push back j equals wrong path. Then I'll construct backwards, so I will reverse in the end. You can construct it from left to right actually, but you need to reverse everything else. It's easier. X plus 1. Again, what I just did is typical dynamic programming. Okay, I just make some bugs. It happens. Because from 0. Okay. Good. So the problem is so this part is just trivial. So I just did trivial dynamic programming. Very typical problem for dynamic programming. Let me show. The problem is that it will time limit. So if you just submit this solution, you will get time limit exceeded. We will check because I don't care about wrong submissions. If you care about wrong submissions, it's better to think about it before you submit. But I will not. So I will have time limit, yes. Why you have time limits? Because you have a bigger resource. So n is up to 10 power 5. Here I have one loop, another loop. So I have 10 power 10. It's too much. So what you need to do, you need to somehow improve this time complexity. Do you hear the dog eating? Okay. Let's close. Oh, okay. My dog's trying to crash one of the cardboards. Okay. She's occupied at least. Okay. Pretty soon she will ask me to go out, but okay. If she's occupied, let's keep it like this. What I will do? I will try to improve this part. So we need to improve this part. So we'll improve the part when we calculate the best jump. And we will do it using data structures. Let's see. So what we're doing here. So we need to take maximum over all elements which have difference at least x. So we have so this our position h of I. Yeah. So we need to step x to the left and x to the right and find minimum for all elements which falls in these regions. Yeah. It looks like a good problem for something like segment tree. The problem is it is segment not by index but by value. So we need to find all elements which value belongs to this range. So I want h of j belong to this area. Yeah. So I want to find all j's such that there find all positions j such that height of the j, height h of j belongs to this region. So I need to build segment tree not by the index but by the value. Okay. The way you do it is it depends on the problem. In different problems you can do it in different way. In this problem, since all values h are pre-calculated, we can do path compression again. So I already talk about not path compression, but value compression today. Yeah. So we will compress all the values of h. Yeah. So let me show you what I'm talking about. So imagine this array. So I have some fixed values of h. So I don't care about all possible values of h. I only care about values 1, 3, 4, 6, and 7. Yeah. So I only care about these points. Don't hear it. What do you hear? Do you hear me? Okay, you must hear me. Can someone answer the chat, please? Okay. Yeah, it's always the same time. Every Thursday at the same time. We started like 2 hours ago. In Discord there is a regular event, so you can check there. You can ask all the questions in Discord if you're interested. So. Okay, so we don't care about all possible values of h. We care about these 4 values of h. So what I will do, I will maintain segment tree only for these 5 values. So for each of these values, I will maintain the best value of xo. So I will best. So I will calculate best d of j for all d of j equals to x. Yeah. And I will for all h. Yeah. So I will look at different heights, and for each height, I will remember the best value of my dynamic programming for this height. And then I will make segment tree over all possible heights. So I will look at all possible heights and make compression. So I will rename them. I will rename this as 0, 1, 2, 3, and 4. After that, I will make this segment tree over these 5 values. And this segment tree will allow me to find the maximum over some segments of the possible values. Okay, let me show you how we do it. Let's go back. So how you do it? You build a segment tree. Let's build a segment tree. First segment tree in this course. Now let's start. So first we will compress all the values. So I will say vals equal h sort Russia uni. I remove duplicates. You don't need this actually, but I will. It will work without it. Just to be clear, actually. Good. So here I just remove all duplicates from this array vals. It actually will not. I can keep these duplicates actually. They don't change anything, but I like to do it like this just to keep everything clear. Now I will create a new array HH. Let's say. And here I will put my compressed coordinates. bound vals p vals and minus what? What's the difference? I'm not sure. I know C-line suggests do it like this. I don't trust C-line. Let's keep it like this. So here I compress my coordinates. Okay, so I do this. I do transformation from. So this is my array H. This is my array H. Now I will do a segment tree, normal segment tree. Let's write segment tree. Okay, you always do it. I have pre-written segment tree, but it's not fun. Let's just so I will initiate segment tree of size equal to my ones. So okay, let's say. So this is the amount of possible values I have. So I will initiate my segment tree of size. Now, we'll replace it. So here I will replace it with finding maximum in my segment tree. Let me check here. So in the okay, let's do one by one. So here, again, okay, let's see. So I need to find this segment and this segment. Yeah. So these segments of elements which are less or equal than hi minus x. So how I do this? I will find the first element which is greater or equal. And find less or equal. Okay, I find element which is greater, so I will find int L equals 2. Again, that's fine. Minus x, let's say plus 1. So L will be this element. So it will be first element out of my range. We can use upper bound. I always use lower bound just for simplicity. Yeah. So it's the first element which is at least this. First element which is out of my segment of interesting elements. I will go maximum of di, and segment tree I will find calc, let's say from 0 to L. Calc will return maximum on a segment. Now I will do the same on the right side. So this element should be the first element greater or equal than hi plus x. Do the same thing. So plus x. I don't like I have plus 1 here but not here, but okay. And the same from R to M. Yeah. M is total number of different values I have. Size of my segment tree. That's all. And finally here, in the end, you just update your value. So I will say update. The coordinate will be hh of I, and you update the value d of I. That's all. Now you can actually, so if you never implemented segment tree before, let's do it like this. Let's implement, before we implement normal segment tree, let's just implement some mock segment tree. So we implement some stupid implementation of this data structure just as a temporary thing. So we'll say t equals t, let's see, assign n-1, we'll put a -1, calculate, we'll say int res equal, we also need to calculate previous value. Okay, I hate this. I calculate d and p. Okay, I need to return pair. Okay. It's actually, it's not pleasant, it's problem. And update. Well, okay, we need again with pair. We'll say equal maximum of ti and like this. So update, I just put the mark again. I maintain the maximal value for each possible I. So when I update the maximum, and here I calculate maximum. Yeah. No, good enough. Okay, so let's fix this. Like this. So I'll calculate pair of value, the value of dynamic prob of levels and the position. So if dd is not -1, it's overcomplicated, and dd plus 1 is greater than di. Okay, you can forget this. Then di equal dd plus 1 and pi equals to pp. And the same thing again for r. Don't like this code, but let's something like this. I believe it should work. Let's try. No. What? What's the problem? There's just warnings. There's a warnings. I don't have warnings. Where are errors? Boom. Oh, here. I misclicked unique. Unique was begin was end. Okay. I like how C++ informs me that something wrong. Okay, it doesn't look like correct. Because I don't. I love C++. When you don't return anything, it just does some strange stuff. Okay. Probably there was one of the warnings was about this. but I just didn't read all the warnings because I'm lazy today. Is it also correct? 3, 4, 5. Good. So now we have correct solution, except we didn't implement the segment tree. So let's implement segment tree, and that's it. That's it. Good. So we're very close. Wrong answer. Wrong answer is unexpected. I expected time limit. Why we have wrong answer? What? What's this? What's this? What numbers do we have? 10 and 15. Okay, it makes sense. So we have really big numbers here. Okay, we need to change everything long again. No, not here. So these heights are long. So we put this. Yes. This X is also long. It doesn't matter. Okay. Again, it's a good thing that we submitted before before we get time limit, because before we implemented the segment tree. Because if we get wrong answer after we implemented segment tree, it would be not clear what happened. Now we have time limit. Nice. Now we have time limit. Good. So let's fix the time limit. To fix time limit, I will change all this implementation with normal implementation. So here I will implement normal segment tree. So how would a segment tree? You make I will do it in boring way. I have pre-implemented segment tree, but I will do it. I will make array of size 4n just to be sure. Here, when I update, so I will update. I will make a recursive call. So when I have recursive call, I have my current node. Let's say node. No, I'll just record node. Let's see. I want to use some short variable, like node, and the borders. And here I will check if I'm in the bottom layer of my array, if r minus equals to 1, then I just update this value. If not, then I check which one I need to go. If my I is less than m, I go to the left part. Else I go to the right part. And then when you go from the recursion, you update your values. So I maximum is t node plus 1 t node t2 node plus 2. Very standard implementation of the update in the segment tree. Okay, if you don't know how to implement segment trees, I actually suggest you to go to my lecture here. I could copy paste code from here. No, maybe not. Okay. I will just implement it. It's fast. Segment tree. So here's a nice. Okay, I usually recommend my own lectures, but it's actually a pretty nice lecture about segment trees. So, I actually I write the same code in this lecture. So, okay. So if you don't know how to implement segment trees, just go here. I explain you perfectly. So here, this is how you update elements in segment tree, and here I need to calculate the result. So I do it like okay. So I'll check if my segment is outside. I return -1 -1. Must find like neutral element. If I'm inside, I return t of node. And if not, then I split in two. Let's return maximum of 2. I call calc from LR node 2 plus 1 to the left and calc to the right. That's all. This is pretty standard implementation of segment tree. So again, when you update, you just go and choose which branch you need to update. When you calculate, you check if you're completely outside, completely inside. If not, then you calculate result in both branches, just take the maximum. Okay, so I added this, so let's add it here, 0, 0, m. So you start from the root, and the current segment is from 0 to m. Not sure, I believe it should work. Can I implement segment tree from the first try? No, I can't. No, I can't. It's embarrassing, actually. No, because I tried to update my code instead of writing from scratch. Okay. Okay. That's why you usually copy the code like this from your pre-written code, so because have less chance of making stupid mistakes like this. Well, that's it. So that's the whole solution. So again, the dynamic programming part is pretty boring. So it's like very standard dynamic programming. But then you need to speed up the solution. So you do it by using data structures, and you think, what data structure can speed up my solution? And like, okay, I need to find some maximums in some strange regions. Can I do it using something like segment tree? You think, okay, I can. Then you do it segment tree. You implement normal segment tree and solve problem. So that's it. That's how we do it. Let's check. So actually, 3 people solve this problem. I'm impressed. So let's check. One of you, let's see who's okay. I never checked you, Roma. Who is it? Yes, that's normal segment tree. Yes, yes. I believe you learned from me. Yes, very similar code. Oh, yeah, no, that's different. That's not how I do it. Okay. Yeah, but overall it's the same. Yes, and here kind of similar thing. Yes, we check this, find all, yeah. And update, like, yeah, the same. And here. Yep. Very similar code actually. And here, you compress all the values like I did. Good. Someone else. Oh, this long one. You use some. Oh, okay, you have some template segment tree. No, why not? Okay, that's good to have some trusted segment tree in your pocket, so you can just take it and use it. Yeah. It's at coder segment tree. Okay, it's not yours. Okay, that's it's not that fun. Just implement your own. It's not that hard thing to do, but then you will understand how it works. Yes, basically. And this go, I believe, does exactly what takes. Here. So yes. So you check if dp is this, then you update. Good. So again, 3 people solved problem. Very proud of you. Any more questions? Okay, we're actually 2.5 hours today. Okay, strange. I expected this. Okay, but that's because I implemented all the tasks. Yeah, it actually took longer than I expected. And that's all for today. So see you next week.